Hi and welcome to MSc. In this video we're going to be looking at VSEPR theory. VSEPR is an acronym that stands for Valence Shell Electron Pair Repulsion. And this is a model that's used to predict the shape of molecules. The main idea here is that electrons in bonds and in lone pairs will want to arrange themselves as far apart in three-dimensional space as possible. So it's the pairs of electrons that repel. And specifically, it's the electrons in those valence orbitals or valence shells, thus the name valence shell electron pair repulsion. Before we go any further with this, we need to stop and define electron domain. An electron domain is a region of high electron density. You can almost think about it as where the electrons live around an atom in a molecule. There's really three possible locations where an electron can live for an electron domain. One is what's called a non-bonding pair, also known as a lone pair. So these are electrons that are not involved in a covalent bond. The next is a bonding pair, just a single bond shared between two atoms. And the last is a double or triple bond. So here we're sharing multiple pairs of electrons. So when we're talking about electron domains, we really have two scenarios. We have these scenarios here, both of which involve bonds, so we call these bonding domains. And we have the non-bonding ones, which are often sometimes called non-bonding domains. And those are really the two options, because for us, a double or triple bond will count as one electron domain, although it will have slight effects on the overall shape of the molecule. There's some key points we need to work through in order to properly understand how to use VSEPR theory. The first is that we need to understand that the repulsion applies to bonding domains and to lone pairs. So lone pairs will push on the electrons in the bonds and vice versa. Again, electrons are negative particles and want to move away from one another. Double and triple bonds, as I mentioned, act as a single electron domain, and that's important when we go to count how many electron domains we have around an atom in order to figure out the shape of the molecule. The total number of electron domains around a central atom determines the electron domain geometry. Now, when we say central atom, it doesn't always have to be just one atom in the middle. It could be one atom in the part of a longer chain or a larger molecule, and we're trying to figure out the shape around that atom. So by determining the number of electron domains, we can start to unpack the geometry of the electron domains and figure out how they're oriented in 3D space. Molecular geometry, also known as like the shape of the molecule, is based on how many of the electron domains that we've previously counted are actually non-bonding domains, right? These lone pairs. So by figuring out how many electron domains there are, I can figure out how they're oriented in 3D space. And then by figuring out how many of those electron domains are lone pairs, that will then tell me the actual shape of the molecule. Lone pairs and multiple bonds have greater repulsive force than just a single bond. And this is because of the electron density, right? So multiple bonds have multiple shared pairs in between two atoms and thus have a higher region of electron density and will exert a bigger force pushing things away from it. And lone pairs have a higher electron density because those electrons aren't spread between two atoms. They're located in a smaller region of space, therefore exert a greater repulsive force on single bonds. So the order of kind of force that we have here, single bonds will repel the least, multiple bonds will repel more, triple more than double, and then lone pairs will repel the most. So when we go to use VSEPR, there's a series of steps that we need to use in order to predict the shape of the molecule. First and foremost, we need to draw out the Lewis formula. You might also call this the Lewis structure or the Lewis dot diagram. That in and of itself is a skill, and it needs to be drawn first. So if it's not already drawn for you by the question, that needs to be the first step. Then we need to count the number of electron domains around the central atom. This will give us the electron domain geometry, as I previously mentioned. Then you're going to determine how many are bonding domains and how many are lone pairs. This will give you the shape. And then you're going to look for lone pairs and multiple bonds to further predict the bond angles. So you'll have standard bond angles that come with your molecular shape or electron domain geometry, and then you'll get distortions to that based on the lone pairs or multiple bonds present. I hope you found this brief run through of VSEPR helpful. Check out further videos to look at applying this in scenarios of 2, 3, 4, 5, and 6 electron domains. If you have found this video helpful, please consider liking the video and subscribing to the station. And as always, thank you very much for listening and watching.